Good afternoon all. To start the scientific session 2, I would like to call upon Professor Pralay Kumar, Professor, Department of Physics, Tejpur University, to kindly chair the session.
Okay. Thank you so much for this opportunity to conduct the technical session. So this technical session 2 is comprised of 6 talks, 1 invited talk and 5 contributory ones. So first speaker is Professor Santabrata Das, and as per your schedule, so just before 1 minute I will stand up. Okay. So stage is yours, please sir.
Okay. Thank you very much. It's really difficult to speak just after lunch. Everybody is requires a bit of need. Okay. So I'll be talking about on this relativistic hot accretion flow around black holes. Looking at the varied audience, I will keep my presentation very lucid so that at least 20% of my talk you can understand. And at the end, I'll explain you the possibilities of utilizing this model in some of the observational facts that we are really curious about. Okay, so these are some of my collaborators, not all, few are in the list. He is my postdoc, now I think he's joining in China. These are two collaborators in IIT Guwahati, and this is one of my oldest friends, and this is VIII from ISRO, and he is my graduate student. So I'm sorry, I'm not able to use my laptop, so many movies will be missing. It's a PDF format. So basically, with this, I wanted to tell you, this is a picture you will often see if you do the Google just by searching black holes. Actually, black holes are very fascinating object. The reason is this is the most simplest object in the universe. If you want to understand the black hole, you need two parameters, mass and speed. Hardly you have any other objects in the universe which you can talk about only with two parameters. So in that sense, is the one of the simplest object, and black holes are having some additional features. By definition, they are black. Nothing can come out. So considering this fact, if we talk about the detection of black hole, we have to rely on its surroundings material that are continuously emitting radiations in the entire electromagnetic spectrum. So in a way, we can consider that the black holes are the cosmic laboratory where we can test many physics, microphysics to the macrophysics all together. So the target is, if there is a black hole, obviously this is not the true picture, it's the artist visualization. If there is a black hole sitting here with its strongest gravity, possibly proportional to the mass, if we do not consider spin at the first place, it strips some of its material, components matter in the form of tidal disruptions, and the accretion disk is formed because of the angular momentum distribution. And this kind of situation happens, and occasionally we can see the very streamed collimated jets are coming out from the environment of the black hole. So within this framework, it is possible to talk about what is the black hole spin and what is the black hole mass. So we will be focusing only on to this topic. Our entire motivation will be based on that, how to talk about a black hole mass or a black hole spin. Okay, so very simple physics, +2 level physics. If you have a gravitational potential energy, something like that, if you convert it to the kinetic energy and then to the thermal energy contributes to the photon energy. So this is the way we can correlate how the energy channel works. Obviously, these are the guideline, because if you look at the entire potential energy available in your pocket cannot be equal to h nu, it should be multiples of h nu. So I'm just, don't be misled with that. Now the thumb rule is, if r is small, then this number will be large. This is a thumb rule. So if the object is really compact, means if you can reach very close to the center of the object, then this can be very large. If this is very large, you have available energy to you is very large. That energy you can emit in the form of electromagnetic radiations, and the energies of those photons will be extremely large. And usually that happens for black hole binaries. Typically we see the distribution ranging from very soft X-rays to the high X-rays, and sometimes in gamma rays. Now, if you focus very close to this region, very narrow region, maybe within 1,000 gravitational radii or maybe a few thousand gravitational radii, the boundary conditions for black hole goes like this. At the horizon, we all know that by definitions the flow has to be entering into the black hole with the speed of light, comparable to the speed of light. That means it must be supersonic. And at the outer edge, for example, here or some, it's coming into the domain of black hole gravity, the velocity must be very small, so it will be subsonic. So the outside the velocity is subsonic, at the horizon the velocity is supersonic, so there must be some transition. Some point is there, the velocity is changing from subsonic to supersonic. Okay, so that transition radius is usually called as the critical points. And to address this kind of picture, this is the picture we understand from the boundary conditions of the black hole system. Now, this kind of situation can be visualized by using many models. People are giving different theoretical models starting from early 40s. So some of them are very popular, like thin Keplerian disk model, thick disk model, slim disk models. And recently people are talking about, recently means last 20 years or so, people are talking about advected accretion disk. So in this topic I will try to address only the last part. As time is short, is very difficult. Each topic takes more than few lectures, so I will not go into the details. So I will confine my talk considering this topic. Now, the standard disk model started with the concept of explaining the luminosity of quasars. These are the two pioneers who coined this topic. So the disk characteristics is very simple. If there is a black hole sitting here, you can imagine there is a rings of matter, concentric rings of matter. Matters are rotating with differential velocities, so there will be a friction between them. Viscosity will be generated. So the disk characteristics is something like that. The matter is Keplerian. It will be very cold, and since the viscosity is is there, even if it is rotating with Keplerian velocity, there will be very little advection with this. And with this, the matter will be driven slowly towards the black hole. And these kind of pictures, it successfully explains the thermal black body spectrum. You can visualize a black hole is sitting here. These are the concentric rings of matter. If you look at its temperature distribution, it gives you a monotemperature disk. And because of the multiple thermal black body, effectively you get a salt bump here. Interestingly, these disks is truncated at 3 Schwarzschild vectors. So that means the matter has to stop at that point. Theoretically, this might be an acceptable scenario, but in reality, if you truncate your disk at 3 Schwarzschild radius, matter is not really falling into the black hole. So some kind of theoretical estimate is here. So if we do a theoretical modeling considering a disk-like structure here, this length is something about, let's say, 10 to the power 4 Schwarzschild radius. If you do a hydrodynamics and calculate the sound speed, this is a very important quantity in fluid dynamics that basically transfers the information from one point to the another point. And you see, this quantity is combination of many things, but within this square bracket, there is a negative sign between these two quantities. This is the flow angular momentum per unit mass, and this is the Keplerian angular momentum. Now, if this quantity is negative, then this fellow will be a complex number. Sound speed cannot be complex, right? So this essentially tells that if you have a sound speed distribution from the outer edge to the event horizon, angular momentum has to be always less than the Keplerian angular momentum. And this is the distribution of this. This broken line is the distribution of Keplerian angular momentum. You see, these are the angular momentum distribution of the flow as you increase the viscosity. So everywhere it is below the Keplerian angular momentum. So Keplerian angular momentum is the meaning like flow will move faster than the Keplerian disk. And since it is moving faster, it will be slightly hotter than the Keplerian disk. Okay, this is the background structure. Then the success that standard disc gave, that brings some additional trouble. What is the trouble? You see, this is the spectra of Cygnus X1. The standard thin disc can successfully explain this part. This is the black body distribution coming from the thermal black body. Additionally, this power law component that you can see here, this component cannot be explained by standard thin disc. So then people are thinking about how to address this question. It was Tita Chuk who coined this turning point. He assumed that, let's say, in the disk there are some location where the temperature of the electron is very high. So if this is the case, you all know what is the comptonization process, right? Comptonization process means there is an electron sitting somewhere, a photon will come, photon will interact with it, exchange energies, the electron will lose energy, photon will gain energy. So the soft photons that you are getting from this Keplerian disk, if there is a hot electron bunch sitting somewhere, that can energize those photons. So that can create high energy radiations. You see, high energy radiation means you can generate this part. It's a kind of a secondary process. So considering that fact, there are many speculations of Compton corona. Compton corona means the corona that can produce Comptonized radiation. Then how to produce it? There are many speculations. Somebody feels that there are different bulge of corona sitting here. Somebody distributed it over the top of the Keplerian disk. Something like this combing structure is also possible to make a model. These all things are coming in as a speculation because everybody tries to explain the observational data. Now, when you are explaining the observational data, people really do not pay enough attention for the theoretical perspective, whether it is a physically acceptable model or not. Okay. But this is acceptable. I mean, the data has to be explained at the end of the day. The data is a raw data and there is nothing wrong in it. So these are the different possibilities. Then there is an interesting part. It automatically comes from the theory which was really lacking until 1989 or so. It's like that. This physics is also very simple physics. So when matter is falling inside the disk towards the black hole, it's rotating, right? You all know what is the centrifugal force. Centrifugal force is a force which acts outward and gravity acts inward, right? Now if you plot these two forces, this blue one is the gravity force and red one is the centrifugal force, then you will see, depending on the angular momentum per unit mass, these two forces can be like this. If you are very far away from the black hole, then gravity wins. If you are very close to the black hole, again gravity wins. But at the intermediate region, somewhere here, you see these two forces are comparable. What essentially it means, the flow wants to fall into the black hole because of the centrifugal rotation or centrifugal repulsion, it cannot. And all matters are traveling in a speed which is greater than the speed of sound. What is the meaning of it? I'm talking to you because my voice is reaching to you with the speed of sound. Now if you move in a speed which is larger than the speed of sound, how loud I speak, you cannot hear it, right? If you move faster than the speed of light. So what exactly happens? When matter is falling from the outer edge, once it becomes supersonic, whatever is happening, no matters, you cannot tell this information to your fellow friend that there something is happening there, don't go there. Because you cannot communicate. So there will be a continuous flow of matter, and because of the centrifugal barrier here, the supersonic matter will go and sit there and there will be an accumulation of matter. You understand this process? It's very simple physics. If this process is acceptable, then how long this accumulation can take place? Accumulation of matter cannot take place indefinitely, right? You cannot earn money according to your use continuously, isn't it? There is a limit for that. The physical limit is, if you look at the density distribution of matter inside the disk with time, there will be a breaking point, just like a toppling of sands in the sea beach. If you go to the sea beach, keep accumulating sands one by one, at certain point, if you add one sand, everything will break down. This is the toppling of matter. So once this density part of a density profile becomes, it exceeds some breaking limit, everything makes a discontinuous transition. In fluid dynamics, it's a very common phenomenon. It's called the shock transition. And if shock transition happens, what you can expect? The density will increase because of the shock compression. Velocity will be slowed down. And if velocity is very slow, density is very high, from the thermodynamics point of view, the interaction will be more, the temperature will be high. If temperature is high, the gas will be puffed up. Right? This is the common plus 2 level physics. If this is the case, then you can expect there is a disk outside the far away from the horizon, and some kind of puffed up region you can expect, and this naturally happens in advection accretion domain, and which is called the post-shock corona. And what happens? This post-shock corona, this movie will not work. It's a PDF file. I'm sorry. This post-shock corona is possible to generate from the numerical simulation. Okay. Now, what exactly happens if you take the soft photons from here, means the photons with a low energy, then there is a chance to interact with a very high energy electron here. You see that if there is a floor, some bulge is there, so some amount of soft photon will go there just to interact, because photons are emitting isotropically. If it goes there, depending on its density and temperature, it will interact with many electrons. There will be a lot of reprocessing. So a soft energy photon, after reprocessing, it will produce a high energy photon. And once it comes out from the entire system, you can detect it, and it may produce the power tail that I explained for the Cygnus X1. Okay. So these are the shock scenarios in astrophysics. You can see the supernova explosions in the bow shocks. In some of the bow shocks, you can see this is a common phenomenon in astrophysics. The shock one is. So this is the structural differences in terms of cartoon diagram. So the low energy photon interact with high energy electron here, and it will produce very high energy radiations. And earlier, the Keplerian disk was a monotemperature disk, and this one will produce a torus-like structure, just like a torus around the black hole. And this torus is effectively behaves like a boundary layer. In fact, people say that the black hole doesn't have a boundary, but this centrifugal repulsion creates something around the boundary, so matter directly cannot fall there. Okay. So the observational part. How much time I have?
Only 10 minutes.
I have 10 minutes. Okay, I'll try to finish. Again, this one is not working. This is a movie. Now, let me explain this. Right now, by any means, if you can oscillate this region just like a bellow action, for some reason, let's assume that maybe a kind of resonance, that if you walk in the bridge and you make some characteristic resonance there, the bridge starts to oscillate, right? Let's say this kind of situation may happen here because of some physical activities. Then the source of the hot electron will oscillate, right? If source of the hot electron oscillates, then the emergent radiation will also periodically vary. The kind of photons will emit from that region, they also oscillate. If you have a detector, you will measure that what is the photon is coming to you in terms of time. So you will see that the photon variations is also not steady, it is varying with time, because this fellow is oscillating like that. Okay. Now, if you want to look at these time series data of photon, and you calculate these power density spectrum in Fourier space, the frequency of this oscillation will give you a peak, the extra power you can find here. Okay, so that can be explained through this shock oscillation model, and at the same time, you can see the different spectral states for the same black hole in few days of time interval. So what happens, let's say if you tune the accretion rate of the matter, which is basically fitted to the black hole, by means of supply of matter from the companion, or by tuning the viscosity that really controls how the accretion takes place. So it is the matter of accretion rate which can control so that it will be a hard state, soft state, or intermediate states. For example, in this intermediate states, from the soft state, this fellow will not be present. It will be completely evacuated. For example, if you can evacuate this region in the form of jets, this corona is absent. See, and it is true that during the jet detection, QPO frequency is not seen. So if the central part is missing, which is possibly the responsible entity for this QPO, so it is possible with this model. Okay. And when it is a hard state, this Keplerian distribution or soft front distribution is so low, it is dominated by the coronal ejection, coronal emission. Okay. So these are the spectral scenarios we can explain through this. And by the way, if you are interested, I have these movies I can show you after the lecture. It's in my laptop, how we can explain it. Now, the study of the shock in general relativistic scenario is very important, because you all know in your undergraduate course or in the postgraduate course, you have learned the general relativity, right? The black hole has to be explained using the theory of general relativity. So, we have done this, and we also realize that the ideal equation of state, where people generally use the mono adiabatic index, the constant adiabatic index, this is not really working. The reason is the temperature of the disk very close to the black hole, it exceeds 10 to the power 9 Kelvin, and outside it is 10 to the power 5 or 10 to the power 6. So there is a temperature distribution maybe of 3 to 4 orders of magnitude. And in terms of basic thermodynamics, you see that if the temperature fluctuation is 4 order of magnitudes, how the same equation of state can represent the accretion disk? It's not possible, right? So temperature dependency is important. So we adopt the equation of state, which depends on temperature. It looks like a very messy expression. It's really not very messy expression. This is the equation of state. And with this, we realize that the accretion solutions that we are talking about, if you vary the energy of the flow and angular momentum, you can subdivide the entire region with 4 categories. For example, if you take parameters any point from here, you will get a solution like this. This is the outer critical point, this is the accretion solutions. If you take any parameter from this region, you will get this kind of solutions. So I will not go into the details of this. These are more technical things. So what is important is we have exercised all those things using ideal equation of state and relativistic equation of state, and you see that the solutions are differing by quite large. I mean, it's something about almost an order of magnitude difference is coming here. So we should not rely on any calculation based on the ideal equation of state, and you can see that's how the adiabatic index is changing for relativistic equation of state. Now, I'll briefly touch upon 2 implications of our calculations, of our formalism. One is how to explain the core radio emission from black hole sources, and another is QPO frequency and luminosity for black hole ULX sources. So, this is the first one. What we did here, around this corona region, since there is a temperature difference, so there is a possibility that some amount of energy will come out. It's a very simple physics. If you have a temperature gradient around you, so some amount of heat energy will immediately go away, right? So we try to model it using this relation. This is the temperature difference, and you cannot radiate all possible energy available to you. You will all be able to radiate only a fraction of it. So beta is the fraction. Now if you add this part in your calculation, you will see that as the energy is coming out from the disk, so your size of this post-shock corona is decreasing. So this is the size. This is the size for the post-shock corona. Now what happens with this process? We calculated what is the maximum amount of energy you can extract from the disk in terms of black hole spin. So as the black hole spin is increasing, you see almost 4% energy you can extract from the disk. If you utilize this 4% energy in the form of shock luminosity, and you can place it in the luminosity and black hole mass plane, you see the black hole mass is varying 10 orders of magnitude. And the radio emissions which is being observed for those sources which is not really separated from the core, all these energies, all these radio luminosities are within these green bands. This green band is calculated using this relation. So our model is capable of explaining the emission of core radio photons for all kinds of black holes, stellar mass black holes, intermediate mass black holes, and also the supermassive black holes. So this is the one important outcome it came out from our result. And this is the second part I want to discuss is the quasi-periodic oscillations and luminosity, and it's 1 minute or 5 minutes?
1 minute.
1 minute. Okay. I'll quickly finish it up. So there is a very simple physics present here. So you all know the infall time scale, right? If I throw a matter at certain velocity, it will take some time to reach somewhere. If I assume that in the post-shock regions, a parcel of matter is falling to the black hole just due to the influence of gravity, this is the relation of infall time scale, just dr over the velocity. It's simple physics. And this should be comparable to some frequency if you inverse it. Now, this QPO frequency and this luminosity, this amount of photon that is coming out, if you calculate for different accretion rate range, these are the values you can get. Since I have limited time, I cannot go into the details of it, but it is possible to calculate what would be the range of frequency, what would be the range of luminosity, you can calculate that from there. Okay, now what we did, we picked up one ultraluminous X-ray source which shows the beautiful quasi-periodic frequency features and also the spectral features, and from there we use our method, our formalism, and we estimated the black hole mass in terms of the accretion rate. So for this source we found that it accretes super Eddington rate if the mass of the IC source is less than 100 solar mass, and these features is maintaining a well correlated relation between black hole mass and the accretion rate through the spin of the black hole. Now we extended this formalism to many more black hole sources like this, where we can find the QPOs and the black body and the spectrum, and we find these correlations in terms of black hole mass and accretion rate. So these are the range of black holes, black hole masses if the spin is very weak and the spin is very high, rapidly rotating. So these are the 5 more sources we calculated it. So with this, anyway, I will stop it here. Time is not really permitting. So anyway, if you have any questions, I will be happy to answer your questions.
Thank you, Professor Dutt, for his well-organized, informative talk. It's now open for discussion. So questions are welcome.
What is the distance range for this particular samples which you have taken?
This distance?
Yeah, distance.
I'm very sorry, I don't remember this. If you want, I can tell you looking at my document.
Megaparsecs.
I think so.
Because you have the spin and all.
Yes.
So this extremely rotating black holes, the mass goes down.
Yes.
Why?
That one of the reason is if the black hole is rotating, then see essentially what is the plot? Plot is if you know the luminosity, if you know the QPO frequency, these two quantities we have to calculate from our formalism. Now if black hole is rotating, now this QPO frequency, if you want to produce, the size of the corona has to be small. And if size of the corona is small for rotating black hole, the mass you don't need very high values.
Can we test the no-hair theorem from your analysis?
Difficult because the reason is here we are using some kind of radiation process. Radiative transfer business is present. So if you use the analysis very close to the black hole, it is difficult. I mean, it's a mathematical challenge is there. Theoretically, it is really possible, but we are not really sure how to tackle the formalism at these regions, very close to the black hole.
Is there any more question? If no, I want to ask one simple question.
Yes, sure.
So you have used idealized equation of state, right?
I didn't use idealized. I used the relativistic equation.
Okay, no, but you said even with ideal equation of state, then you have applied relativistic correction over the same or relativistically corrected equation of state.
Relativistically corrected equation of state.
Okay. So is this the most judicious as of now?
Yes, because the temperature profile is quite large. As I said, this minimum is 10 to about 3 or so. Even it can be higher. So if you use the same ideal equation of state, then the adiabatic index will be constant, and that really not feasible because close to the black hole temperature is very high. You have to take care of the relativistic effect. You cannot ignore it. Outside it is possible, but not very close to it.
Okay, so let us thank the speaker once more for his wonderful talk. Okay, thank you. And next speaker is Ritik Bora, and his talk will be on correlation study of spectral parameters using simultaneous multi-wavelength observations of MKN 501. Okay, please.